Hello students, this is Usha from G.K.Jain High Secondary School. Today we are going to see electromagnetic induction and alternating current part 3 in 12th standard physics. So in this topic we are going to see about the self-inductance and the mutual inductance. Let us watch the PowerPoint presentation. Electromagnetic induction and alternating current part 3. Self-induction. Inductor is a device used to store energy in a magnetic field when an electric current flows through it. The examples are coils, solenoids and toroid. Inductance is the property of inductors to generate EMF due to the change in current flowing through that circuit. Self-induction. Whenever a electric current flowing through a coil, magnetic field will be produced around it. Therefore, the magnetic flux of the magnetic field is linked with the coil itself. If the flux is changed by changing the current, an EMF is induced in that same coil. This phenomena is known as self-induction. The EMF produced is called as self-inducted EMF. Let phi-b be the magnetic flux linked with each turn of the coil of n turns. Then, the total flux linked with the coil will be given as n into phi-b. It's proportional to the current I in the coil. So, n phi-b is directly proportional to I. To remove the proportionality, introduce a constant L. So, n phi-b is equal to L into I. L is equal to n phi-b divided by I. L is called as self-inductance of the coil or coefficient of self-inductance. If I is equal to 1 ampere, then L is equal to n phi b. Self-inductance or simply inductance of a coil is defined as the flux linkage of the coil when 1 ampere current flows through it. When a current I changes with the time, so an EMF is induced in it. From Faraday's law of electromagnetic induction, this self-induced EMF is given by epsilon is equal to minus d phi by dt of n into phi b. So we have already derived that n into phi b is equal to L into I. So we have d minus d Li divided by dt. Therefore, epsilon is equal to minus L into di by dt because L is a constant, or L is equal to minus epsilon divided by di by dt. The negative sign of the above equation means that the self-induced EMF always opposes the change in current with respect to time. If di by dt equal to 1 ampere per second and then L is equal to minus epsilon, inductance of the coil is also defined as the opposing EMF induced in the coil when the rate of change of current through the coil is 1 ampere per second. Next is unit of inductance. Inductance is a scalar. Its unit is Weber ampere inverse or volt second ampere inverse. It is also measured in Henry. The dimensional formula of inductance is m L square t power minus 2 a power minus 2. So the inductance of the coil is 1 Henry if a current changing at the rate of 1 ampere per second induced an opposing EMF of 1 volt in it. Physical significance of inductance. So the inductance plays the same role in a circuit as mass and moment of inertia play in mechanical motion. When a circuit is switched on, the increasing current induces an EMF which opposes the growth of current in a circuit. Likewise, when the circuit is broken, the decreasing current induces an EMF in the reverse direction. This EMF now opposes the decay of constant. So that is shown in the diagram. The next topic is self-inductance of a long solenoid. Consider a long solenoid of length L and cross-sectional area A. Let n be the number of turns per unit length. When an electric current I is passed to the solenoid, a magnetic field is produced which is almost uniform and it is directed along the axis of the solenoid. The magnetic field at any point inside the solenoid is given by B is equal to mu naught Ni. As this magnetic field passes through the solenoid, the windings of the solenoid are linked by the field lines. The magnetic flux passing through each turn is phi b is equal to integral of A B vector dot dA vector. So B vector dot dA vector is equal to BA cos theta, which is equal to BA because theta is equal to 0, cos 0 value is 1. So mu naught Nia is the value for the phi b. The total magnetic flux linked or flux linkage of the solenoid with n turns is given as n phi b is equal to nl into mu naught Ni into A, substituting for phi b from the above equation. N phi b is equal to mu naught n square Al into I. So we'll get n phi b is equal to Li. So comparing the equation, we'll get L is equal to mu naught n square Al, or L is equal to mu naught n square Al. Mu can take a value if a dielectric medium or relative permeability mu r is being substituted. Then L is equal to mu naught mu r n square Al. This is the equation we will get as the last one. Next is energy stored in an inductor. Whenever a current is given to the circuit, the inductance opposes the growth of the current. So, when a current in the circuit is being given, work is done against this opposition by some external agencies. This work done is stored as magnetic potential energy. So assume that electrical resistance of the inductor is negligible and inductor effect alone is considered. The induced EMF epsilon at any instant t is epsilon is equal to minus L into di by dt. Let dW be the work done in moving a charge dq in a time dt against the opposition. Then dW is equal to minus epsilon into dq. So we know that dq is equal to I into dt. Substituting the value will get minus epsilon I into dt. Substituting for epsilon, which we derived in the above equation, epsilon is equal to minus L into di by dt. We'll get dW is equal to Li into di. So total work done in establishing the current is W is equal to integral of dW, integral 0 to I Li into di. L is constant, we'll take it out. Using an integral formula, integral of x power n dx is equal to x power n plus 1 divided by n plus 1. Instead of x, we'll have here I. So substituting the value, I'll get L into I square divided by 2, applying the limit 0 to I. So we'll get the work done as W is equal to half L I square. This work done is stored as magnetic potential energy. UB is equal to half Li square. The energy density is the energy stored per unit volume of the space, and it is given by UB is equal to UB divided by AL. Therefore, volume of the solenoid is equal to AL. So, UB is equal to Li square divided by 2AL. Substituting for L value, mu naught n square A into L into I square divided by 2AL. Cancelling A and then L, we'll get mu naught n square I square divided by 2. But we know that B is equal to mu naught Ni. So you'll get UB is equal to mu naught Ni. The next topic is mutual inductance. When an electric current passes through a coil changes with the time, and EMF is induced in the neighboring coil. This phenomena is known as mutual inductance, and the EMF is called mutually induced EMF. Consider two coils which are placed close to each other. If an electric field I1 is sent through coil 1, the magnetic field produced by it also linked with the coil 2 changes. Let phi 21 be the magnetic flux linked with each turn of the coil 2 of N2 turns due to the coil 1. Then The total flux linked with the coil 2 is proportional to the current I1 in the coil 1. So we have N2 phi 21 is proportional to I1. N2 phi 21 is equal to M21 I1, or M21 is equal to N square phi 21 divided by I1. The constant of proportionality M21 is the mutual inductance of the coil 2 with respect to the coil 1. It is also called as coefficient of mutual inductance. If I is equal to 1 ampere, then M21 is equal to N2 phi 21. Therefore, the mutual inductance M21 is defined as the flux linkage of the coil 2 when 1 ampere current flows through the coil 1. So, when the current I1 changes with the time, an EMF epsilon 2 is induced on the coil 2. Same way how we derive for the 1, the 2 also can be derived. So we'll get epsilon 2 is equal to minus d n2 phi 21 divided by dt. So minus d by dt of m21 I1. So minus m21 into di1 divided by dt, or m21 is equal to minus epsilon 2 divided by di1 divided by dt. The negative sign in the above equation shows that they are mutually induced EMF always oppose the change in current I with respect to time. So, the unit of mutual inductance is also Henry. Mutual inductance M21 is also defined as the opposing EMF induced in the coil 2 when the rate of change of current through the coil is 1 ampere per second. The mutual inductance between two coils is 1 Henry if a current changing at the rate of 1 ampere per second in coil 1 induce an opposing EMF of 1 volt in coil 2. The next topic is mutual inductance between two long coaxial solenoid. Consider two long coaxial solenoid of same length L. The length of the solenoids is larger when compared to their area or compared to the radii. Then the magnetic field produced inside the solenoid is uniform and the fringing effect at the ends may be ignored. Let A1 and A2 be the area of cross-section of the solenoid, with A1 being greater than A2. The turn density of this solenoid are N1 and N2. Let I1 be the current flowing through the solenoid 1, then the magnetic field produced inside it B1 is equal to mu naught N1 I1. If the field lines of B1 passing through the area bounded by solenoid 2, the magnetic fluxes linked with each turn of solenoid 2 due to the solenoid 1 is given by phi 21 is equal to integral of A2 into B1 vector into dA vector, which is equal to B1 A2 since theta is equal to 0. So we get the answer mu naught N1 I1 into A2. The flux linkage of the solenoid 2 with the total turns N2 is N2 phi 21 is equal to N2L into mu N1 I1 into A2 since N2 is equal to N2L. N2 phi 21 is equal to mu naught N1 N2 A2L into I1. So substituting the value we'll get this answer. From the above equation we get N2 phi 21 is equal to M21 I1. So comparing both the equation we'll get M21 is equal to mu naught N1 N2 A2 into L. This gives the expression for mutual inductance M21 of the solenoid 2 with respect to the solenoid 1. Similarly, we are able to find out the mutual inductance M12 of solenoid 1 with respect to solenoid 2 as we are done for the above cases. Same way, B2 is equal to mu naught N2 I2. Same way, phi 12 equal to integral of A2 B2 vector into dA vector, which is equal to B2 A2, which is equal to mu naught N2 I2 into A2. Then the flux linkage of solenoid 1 with the total turns N1 is N1 phi 12 is equal to N1 L into mu naught N2 I2 into A2. So N1 phi 12 is equal to mu naught N1 N2 A2 L into I2. So we get M12 is equal to mu naught N1 N2 A2L. Comparing the equations, right, we'll get M12 is equal to M21 is equal to M. So, in general, the mutual inductance between two long coaxial solenoid is given by M is equal to mu naught N1 N2 A2L. If a dielectric is being applied in between them, then we have mu naught mu R N1 N2 A2L. You all have learned about the self-inductance and mutual inductance. Now, before I end this session, I would like to speak few activities that we conducted in our G.K.Jain schools. Band class and Bharatanatyam class were actively conducted in our school. The admission for the academic year 2020-21 is going on, and for further enquiries, you can contact our websites gkjainschools.com.